This conference will now be recorded.
Hey guys, we'll be starting soon. While you're waiting, just make sure that you have a Kaggle account so you can check out the code.
Wait, Yash, you wanna put the intro slide up?
Oh yeah, I got it. Look. Once. Yeah. Hold on. That's good now.
Okay, everyone, for those of you who are coming in early, make sure you create your Kaggle account at kaggle.com if you haven't already.
Yash, quickly check executive.
Oh yeah, I got it. Yeah, Andrea got it.
Huh? Hello. Hello. Okay, hi everyone. It is now 3:03 on the Pacific time or 6:03 on the East Coast. So we're going to get started with our Intro to AI workshop series. Thank you all for signing up and coming today. And without further ado, welcome, and we're going to get started. So reminder to create a Kaggle account at kaggle.com if you haven't already. It's a free account and takes like a minute to sign up. So please do that. There will be a little bit of Python knowledge that would be required to get the most out of this class. However, if you know only a little bit, you'd still be able to get the conceptual understanding of AI. And how this is going to work is the schedule is on the screen right now, screen shared with you. So first we'll have an intro to AI presentation by Yash for the first 30 minutes. We'll have a coding tutorial with Eban from 3:30 to 4:15. We'll have a quick Q&A session. And then after the class, you're welcome to work on extensions on your own time and ask us by email if you have any questions, or you can ask on Discord. The next day on Sunday, we'll have a coding tutorial by Pranav from 3 o'clock to 3:45, Q&A from 3:45 to 4 o'clock, and we have a special guest at 4 p.m. who is Krithik Ramesh. He's the 2019 ICEF grand prize winner, and ICEF is the most prestigious science competition for high school students, and he won $75,000 for his work. So he used AI and biomedical engineering together. So this is a really great opportunity for you guys to learn about how AI can be applied successfully. Yes, and at the end, we'll send out a quick feedback form. Yash, you can go on. Yes, and then next. So this event was organized by the Helyx initiative in conjunction with DMV Hacks. So we're based in the West Coast and you're based in the East Coast. So this is a great collaboration. So what we at Helyx do is we essentially spread STEM education online and in person, but mostly online now. If you're interested, you can join us on Discord at helyxscience.org with Helyx with a Y, or visit our website helyx.science. So about us, we have 750 members in 29 chapters and in 14 countries around the world. We do STEM outreach, free workshops like this one, blog writing, editing, research program. We match you with a mentor. For example, many of our research program participants have been matched with mentors from MIT or Cambridge and Oxford. Additionally, we also run science contests, a YouTube, TikTok, and podcast channel. And we are hosting events such as the International Youth Research Summit this June, June 20 to 21. And that is where 200 students from around the world will come together to share their work and discuss science with each other. We're also hosting a special research science fair where you can actually win money for your project, details coming soon. and we're hosting a bioinformatics summer camp this summer and a hackathon in the winter, and we also offer free tutoring year-round. And we're currently seeking new chapter presidents, tutors, writers, editors, and more. So if you're interested, just join our Discord at helyxscience.org. Thanks. And now for Lucy. Oh, wait, sorry, one more thing. Next slide. We're also, so our, oh, okay, I guess not. Yeah, Lucy.
Thanks, Andrew. Hey guys, I'm Lucy and I'm from DMV Hacks. So just like a little intro about DMV Hacks. We're like a nonprofit organization and we're dedicated to providing free computer science education and opportunities to people who are interested. Today, like we are super excited to be doing this workshop with Helyx Initiative. AI is such an important field of CS and it is great to see all of you guys here today to learn more about it. For this workshop, we have Eban and Pranav from DMV Hacks, and they'll be giving AI demos. So if you guys just want to say hi, or like wave or anything, that'd be cool. So just a little bit more about DMV Hacks. We are offering 6 different classes, and we have 100 plus volunteers and 250 plus students. We're located in DC, New York, and California, but we're also expanding more across the US. So about our classes, which are like our spring classes, they feature small group and one-on-one mentoring. We've got Scratch classes, Java classes, Python classes, and we also have web development. We have more opportunities in the summer, and we are excited to share more about that. And if you guys want to register for those free classes, you can check it out at dmvhacks.org. So now Yash is going to be giving our presentation on AI.
Yeah, so before we get into that, another coding event opportunity from Helyx. So as you can see, there's a link below. We're hosting our second hackathon. It's called Nucleotide. So if you go to the link here, which will also sound out this presentation, but yeah, you can sign up and like for our interest letter, and we'll send out more details. But without further ado, the intro to machine learning. So I'm Yash. I'm the Chief Technical Officer at Helyx Initiative. I've been programming since I was like really young and working at like top institutions for AI and working with professors and doing lots of research in AI. So I'm really interested in tech and I'm excited to share what I have with you guys. So first question is like, what is machine learning, right? So you hear it often, but you don't really know what it is. So like one thing that I remember learning or looking at like in this one talk I went to was this quote by Herbert Alexander Simon, which is that learning is any process by which a system improves from experience. So you'll see why that comes in handy later on through like training data and other like just the general structure of how machine learning goes and like how the workflow of machine learning is. But a like pretty textbook definition of machine learning is algorithms that can improve their performance using training data, in this case like experience. Am I echoing? Okay, so examples of like machine learning include like face detection, speech recognition, stock predictions. So we'll talk more about like more examples later, but yeah, machine learning is modeled after this idea of like how computers can only do things with instructions, right? So it's modeled after like trying to make a computer adapt to human intelligence, because obviously we're smarter than computers, and that's led to a lot of like automated tasks like surgery. That's led to like us developing stuff and just like building this like sense of like society like with intelligence. So an example that I like to give is the cat recognition example. So like you wouldn't know what a cat is like unless you've seen a cat and someone will like, that's a cat, and like you would know like the different orientation. So you want to make sure like a computer can do the same thing. So that's like kind of what machine learning is about. So what is machine learning compared to like actual programming? So like an algorithm or something, right? So traditional programming has data, and there's like data in a program that goes into the computer which generates an output. But in machine learning, it's different because it's data and output. So it goes into the computer and then generates a program. It's like a different workflow, but we'll talk more about it as we get into it. So yeah. The next thing is like, what is machine, like you've heard artificial intelligence in like sci-fi movies and like other stuff. But yeah, the difference between machine learning and artificial intelligence is that machine learning is specific to inputting data into a machine so it can learn by itself, while artificial intelligence is like a broad term that's main goal is to make the machine smarter. So a map like I like to use is this one. Like, so artificial intelligence improves from machine learning, and so that's like the main, like machine learning is a build on to artificial intelligence. So that's like a key difference. So they're not the same thing. So why machine learning? Why can't we just program a bunch of algorithms or like use a bunch of if statements and like do stuff, right? Well, machine learning is like the reason we use machine learning is to so for a few reasons. So like first is developing systems that can automatically adapt and customize themselves to customer needs. So if we were to like if someone were to sit there all day and write a bunch of if statements and code, we could like potentially do this, but there's always going to be these adaptations that machine learning just allows us to get through. So a good example, like I saw while making the slide, was LinkedIn skill recommendations based on the rest of your LinkedIn profile. So let's say I put in like a software engineer, then like it would be like, oh, something you may know is like how to do Python or like how to deal with databases. And so it gives you those recommendations. So that's like an adaptation, and that's like based on an individual customer. And you'll learn more about that as you go back into machine learning and start digging in depth. The next thing is discover new conclusions from data and predict. So there are like a few ways I like to put this. So like exploration. So like the main part of like machine learning is like prediction. So good examples like stock patterns. So if like a stock is going down, up, down, up, down, up, down, up, and then like you're like, okay, so it's having this like repetitive cycle, right? And then you use machine learning to be like, okay, so the next cycle is probably going to be this. But that like the initial like down up thing is going to be like your training data. And you'll see that like I'm going to keep talking about that and keep reiterating that and then formally define it, because it's like a really important concept. Training data like allows a machine learning algorithm to like proceed. But the next is as we already talked about, ability to mimic human and replace certain monotonous tasks that require human intelligence. So a lot of like AI and like or a lot of machine learning and stuff that we're going to see in the future is like in industries where computers can be more efficient or can do tasks that like humans can't do, or like even do them that humans can do but take a long time. And we're already seeing that now with like robots in manufacturing industries. And we're also going to start seeing it in like surgery, which a lot of like doctors and stuff are going to like keep working on. So the goal of like computer science and like the goal of just like working with computers and programming has always been like trying to make these computers smarter so we could use them to our advantage. So why does machine learning matter? Right now, every single thing you're doing has data. It either generates data or requires data or does both. Like right now, for instance, you entered this call, that's data. For like the reason you're in this call, that's also there's like a streamline of data. After you leave this call, we will post a recording, that's also data. So like just data flows everywhere, and it's also super important data. And so you want to analyze it, you want to like work with it, and that's like a big part of machine learning. But the next is like automating tasks to improve efficiency generally. Like we're always looking for more efficient solutions as people, and like machine learning is just a step to make computer programming and stuff like more efficient. So the next thing is like the structure and like how machine learning works. I would say this is like a pretty basic like format of how machine learning actually works. So like a basic process would be like, you start out with your training data. It gets put into this learning algorithm, which is I'd say like it's like the meat of the sandwich. It's like the meat of machine learning. So, and then yeah, you like test. So then you use the training data to create the model and like create the algorithm so that like, or to train it so it can. Oh, and then you measure that against some like validation data, which is a different data set other than the training data set. So you can see there's a training data set, a test data set, and then you validate your model using the test data set. And then you see how accurate your prediction is. And you use tools like Kaggle, or like tools like TensorFlow and stuff, but we'll get more into that. So just some basic machine learning terminology. I think I probably misplaced this, but models are essentially validated on an accuracy using like different data sets to ensure like all-around performance. So you don't want it to be super, super good at like getting training data like 100% accurate, but you also want to make sure that it's good at like testing like generic trends, right? Like, sure, if I gave you a blue, like 12 blue things, then you could always recognize that something's blue, right? But if I put in a red thing and you've never seen a red thing before, you're never going to recognize it's red. So you always want to, so a big problem that a lot of scientists and a lot of data science, a lot of like AI engineers are trying to solve is that, is this problem of overfitting. The model is essentially like really, really well trained to this training data, but when it gets off the training data or off these like training wheels, essentially, it doesn't know how to perform. So like the test set is like why you should validate your model, right? And that's like the entire idea behind validation. Underfitting is like when the model is literally just too simple and it just doesn't work. And doesn't work on training or test data. Features are ways to categorize data. So you're gonna like especially in classification, like you're gonna have different ways you can, like pick out parts that are good. So like for instance, you'll see in Kritik's lecture, like he'll be talking about different features about like in biomedical engineering and in his work of like biomedical AI. And then so feature extraction is used to find the most important features for detecting an object, which is like someone's eye or something that's like different, just like those important things. You'll see neural networks, you'll see that in Pranov's lecture and Eban's lectures, and like and then yeah, that's just general for like machine learning. I think those are like the three big ones, but there's definitely a lot more. So here's like a pretty good visual about like how we categorize machine learning. So machine learning like breaks up into these two subparts of unsupervised learning and supervised learning. So unsupervised learning is essentially like you have like this input data and you have to like interpret it and like you group it together. But supervised learning is like you're given, what the output has to be as a human, and then you develop a model so that the computer can also know what it is, as like considering the input data too. And then there's like different ways of categorizing it. So unsupervised learning is like clustering, and then you'll see like classification and regression for supervised learning. Here's a huge list of them. I don't think that like I'm not gonna like go super in depth or like explain these because like it's gonna take a while. But yeah, this is just like just the sheer magnitude of just how many machine learning algorithms it is. And like also one more thing I forgot to say, unsupervised learning is not like supervised learning, despite like knowing the output, doesn't mean it's like super easy or anything. So like they're both still, machine learning is still a pretty like hard thing, and it's like a problem that everyone like has fun trying to solve. So yeah, here is just like a large list of these algorithms, but you don't need to know all of them. And if you get deeper into machine learning, you will know a good amount of these. So where do we see machine learning? So the first place is what I like to call is the automatic email spam filtering. So if you've ever like gotten an email, like, so the way that these things work is the training data is where like you select what spam is, or like you mark something as spam, and then it'll continuously put those things in spam. And then so that's like also how like that's like one example of machine learning. The next is like a Face ID. So if you have like an iPhone X or something, then you have this feature, or like a Windows Hello thing that like unlocks if you have Face ID. It uses facial recognition by like mapping your face, and like that's the training data, right? So when you first get it, it'll ask you to show you your face in like a bunch of different angles, and then it'll use facial recognition to, you know, detect your face every time it sees it again. The smart home assistant, that's like pretty obvious. If you say something, you know, it'll detect it, it'll act on it. That's natural language processing. Self-driving cars or autopilot. We're seeing this a lot in Tesla and stuff, but like for instance, like a Tesla car would detect a speed sign, and it would you know, set your speed limit to that if you want it to. One thing you guys can do if you're interested is just say like, you know, other examples of this in the chat. See, I'm getting, okay, yeah. Okay, cool. Video game bots recommended for you. Yeah, that's a good idea. Yeah, that's a good one. Recommended for you on YouTube. Yeah. So the training data for that would be like how many YouTube videos you watch, and like video game bots would be different, like training data. But yeah. So looks like I'm getting caught on time. But so here's some like tools to work on machine learning, and like Pranav and Eban will like elaborate more on it. So the first is like Python, which is a very commonly used language for machine learning. A lot of people use TensorFlow, which is really popular. Keras is used to develop neural networks. Scikit-learn is also like a mapping. That's more of a conceptual machine learning algorithm. Scikit or PyTorch is also like another kind of thing, and it like aligns with the framework of like TensorFlows and things like that. So Anaconda and Kaggle are both these things that are like Anaconda and like specifically Jupyter notebooks, and Kaggle are things you guys can explore. Pravon will take you through Kaggle and stuff, which are like essentially these like cells where a lot of people work on machine learning and data science, and Kaggle is a good starting place for that. Are there any questions? Just ask in the chat, or just give it a few more minutes. When will the tournament start? You mean the hackathon? Yeah, so that's what the interest form is. Oh, so yeah, the interest form will send you out more details for the hackathon. Chirag, how do you apply biology to machine learning? What areas are usually of interest? So I think that machine learning can be applied in any industry. For biology specifically, there's a lot of ways. So there's medical diagnosis, yeah, so you essentially like look at images of like, let's say a lung image, and then you like can you know, do some analysis on it, which you'll see more, and like Kritik's work will show you some more about like prognosis and stuff. And treatment is like using NLP. You can use like ML to like make NLP like to detect what the doctor is saying, and like have its own write-up, so you're not wasting time. There's like a lot of ways that you can apply like biology to machine learning that we've seen. And what areas are usually of interest? Yeah, again, like I think it's really applicable in anything you could do, and you always just have to find like way and medium if you can like intersect machine learning and the industry. What's the best way to start off with machine learning? What would you learn first, and how do you move forward? So the first thing I would do is like definitely try to understand machine learning at a conceptual level. Actually, I mean, yeah, it just depends on your goals, right? So like, I think for me, I spent time like, well, first always like learn Python. It's just going to be a pain if you don't. So learn Python. That's definitely like the first try die for yeah, it's definitely the first try die for like machine learning. Then to move forward, I would like start working specifically towards data science. Start trying to take courses, like build different projects, like work on convolutional neural networks, do different things like that. Any courses or resources to explore? So I'm like, I have like some document probably somewhere with that, like from Helyx. So I can definitely send it to you. I'm gonna post my email up here shortly. So if you want to email me that and remind me, I can do that for you. How can ML be applied for gaming? So like ML can be applied to game. So like I specifically have not done much work in gaming. That's just not my interest. But I think a lot of ML can be applied to gaming, like like different character settings, different like actions that like CPUs can do. Smarter CPUs that can detect like different player actions and like perform better. There's definitely like a lot of things. What do you get from the hackathon? Okay, again, for hackathon, like we will send out emails for that, and like so don't worry about that. What books or courses do you recommend to learn machine learning? Again, like I can send out a list of resources if you just email me, which you'll see in a bit or in like a second. What programming language is used to create Face ID? So Python mainly, because it's like a convolutional neural network thing. So yeah. Yeah. Okay. I will be here tomorrow. If you have any other questions, here's my okay, yeah. Here's my email. Feel free to email me. Don't like do anything too weird. But yeah. I think that's it for me. So thank you guys for listening. And if you have any questions, of course, I'll try to be at the Q&A tomorrow. And yeah. All right. Thank you guys. Okay.
Thank you, Yash, so much for that introduction. So now we're gonna work on a coding tutorial. So my name is Eban. I am in 11th grade at Thomas Jefferson High School for Science and Technology in Virginia. So yeah, as Yash mentioned, yeah, machine learning is becoming more and more necessary as the data sets get larger and larger. I think there's about like 5 zettabytes of internet traffic. Like, you know how there's gigabytes and like petabytes and whatever terabytes? There are zettabytes now of data in the internet, and a zettabyte is like a trillion gigabytes. So there's so much data, and what we need to do with that data is we need to analyze it using machine learning. So today I'm going to show you guys a smaller, I'm going to show you guys like an example of machine learning using a smaller data set, but it'll be representative of the endless possibilities. Tip of the iceberg. So I made a Kaggle notebook. And I will share you guys the link first. Okay, here's the link for the Kaggle notebook, and you guys can follow along. I will also be sharing my screen. Okay, yeah. Everyone, make sure that you turn off your mic. Make sure you mute your mic so that there's no. Okay, share my screen, and I will show you guys. I think you guys can see it now. So essentially, I created this notebook to explain simple linear regression as well as multiple linear regression. So some of you might know machine learning, a little bit of machine learning already. Some of you might not even know that much coding. So I'm going to try to make it interesting and appealing to all of you. I'm also going to have some discussion questions, so you can answer those through the chat. So yeah, as I mentioned earlier, linear regression is kind of the tip of the machine learning iceberg. There's going to be lots more that you can use. Tomorrow we're going to go through deep learning, and you can also feel free to stay after and discuss with us. So we're going to learn linear regression today, and we're going to use a data set of house sale prices. Okay, I'll show you the data set right now. You click on input here, and you can see the data set that I've created. It's called Regression of House Prices. So yeah, here's the Kaggle data set that I've made. You can see that there's 3 files here. Data description.txt. This is a text file, and it shows it describes each of the column names. This is the column name, and then this is kind of the description. So MS subclass means the type of dwelling, and then it lists all the values. Then you have MS zoning, which is the zoning classification, and you have different code values. These are just the different values. This is for the user. And then we also have a test.csv and train.csv. Here, okay, so essentially a CSV file, it's like an Excel spreadsheet. So if I click on compact, and then if I say select all columns, apply, I'll see that it stores the data for all of the houses. So each row here represents one house, and then each column is the information for that house. So for example, for house 1, it has a classification of 60, zoning is residential low, and then lot frontation is 65, area is 8,000, and so on. So there's 81 columns here for each house. Each row is one house, and then each column, it goes on. Lots of information recorded about each house, and then here's the sale price. So essentially, what we're going to do is we're going to try to predict the sale price given all these details about this specific house. So that seems cool and all, but it's kind of arbitrary if there's no application. So one application of this could be like, if I was a buyer, let's say, if I was a buyer and I wanted to buy a house, I want to buy a house that's quality, but also a good price, right? I don't want to overspend when I buy this house, right? I don't want to buy, I don't want to spend like $500,000 if the house has only like 1,000 square feet of area, right? So you want to be able to find a good trend and compare that house that you're trying to buy with the other houses and see how it compares. And same thing, if I was a real estate agent or a seller, I want to see, okay, how competitive am I? How well am I putting this house sale price at? Is it going to give me a lot of profit, or is it below profit, and so on? Yeah, right. So I'm going to walk you through this notebook from the beginning. So the first step we're going to do is we're going to import some Python libraries. These are called libraries, modules, packages. Essentially, they have many different names, but they all just mean like a collection of functions that we're going to import at the beginning of our code so that we can use those functions later. So this is kind of like importing any kind of package. Like, let's say, it's kind of like importing like an Amazon package, right? So if I want to buy something from Amazon, let's say like, I don't know, a back scratcher, I would have to import the back scratcher from Amazon to my house before I can actually use it, right? So before I can say Amazon.backscratcher.scratch my back, I have to say import Amazon.backscratcher, right? So that's essentially what we're doing here. We have a couple of different Python libraries. The first one here is called NumPy. This is for math. Then we have a pandas library for data processing, matplotlib for plotting figures, cbrin is also for figures, but it allows for like better, cooler visualization. And then sklearn, scikit-learn is, as Yash mentioned, it's generally used for machine learning. So here you can see I coded this. These are called import statements. I say import numpy, which is the name of the package. When I say as, that kind of creates a nickname for this numpy package. So instead of every time I want to use numpy, instead of saying numpy dot whatever, I can just shorten that to np dot whatever. So yeah, I give all these nicknames just to make it easier for me to write. And then I say print. I just want to show you guys what a print statement looks like in Python. So in Kaggle, this is the code. The code is in gray here in this gray box, and then the output is in this black box. So here, this black box shows that it's done importing the library. So now we're going to look at the data that we have from the data set. So we're going to use the pandas library that we imported earlier, and we're going to create a data frame. So a data frame is essentially like that spreadsheet that I showed you, the CSV file, except it's stored in a way that the code can understand it, right? So it's a 2D data structure, and it has each of the rows represent observations, which represent each house, and each of the columns represents the features of each house. So there's 80 columns, 80 features, and we're going to use those 80 columns to predict the last column, which is sale price, for each of the 1,460 observations. There's 1,460 rows and 81 actually, including sale price. So here I create a variable and I say equals. Equals in computer science mean assignment. It doesn't mean equals like equivalence in math. It means assignment. So what I'm doing here is I'm assigning this data frame variable to the pandas.readtv. So right here is amazon.backspactor.scratchmyback. This is pandas.readtv, which is one function that will create a data frame given a input file. So this is my input file, and I do that. Then I say, okay, print the preview or head of this data frame. So you can see here what it looks like. There, okay, let me zoom in actually so that you can see it better. Okay, here we see 5 different rows. When I say preview, head means 5 different rows, and you see all the columns. And it cuts off a little bit because 81 columns is too much to display at once, right? Yeah, so that's essentially what head does. Then this line is really interesting. So what a data frame is, I told you, right, it's a 2D data structure. This is what it looks like. And when I say data frame, when I call it on this column called sale price, it'll store all of the values of that column. So here, sale price, this variable is now going to store all of these values in this column. Understand? And then here, when I say sale price dot describe, that will just print out all the descriptive statistics, so like the mean, the median, and so on. So yeah, there's 1,460. Yeah, you understand. Okay, so now we're going to generate a heat map. The heat map is essentially a visualization that is based on colors rather than numbers, and that's what makes it easier to read. And we're going to do so based on the pairwise correlation of each of the columns. Correlation is like how well do the 2 variables like match. So what I do first here is there's this pandas method called core, and when I say dataframe.core, it will return the correlation coefficients for all of the paired columns, and I'll store in this variable here. This line over here is just to make the graph bigger so you guys can see, and then I'll use the SNS heat map to map the correlation matrix with a mid value of -0.7, a max value of 0.7, and a color map of red and blue, and then I plot them as squares. So this is what it looks like. You see, it goes from -0.7 to +0.7, and this is the correlation between each of the variables. You see, this variable here correlates to this variable here. I'll zoom out so you guys can see it better. And so yeah, this is essentially what a heat map looks like. And what I want to ask you guys is, what do you notice about this heat map? What do you notice about the heat map? Sorry, I can't see the comments or the chat box. Oh, here. Yeah, exactly. The diagonal, that's the first thing that you should notice about the heat map. But what does that mean, you know? Exactly, Alex. Yeah, that's exactly what it represents. So a darker value, if you see on the right side of the screen, a darker value corresponds to high correlation, right? So high correlation is because, yes, exactly, Dante. What it means is that if you look carefully, you can see that all of the values on the y-axis are also plotted in the same order on the x-axis. So ID over here is also plotted as ID over here. So you'll see that when you plot two variables against themselves, it's just a one-to-one correlation, yes, like Dante said. And then that's why there's a blue diagonal over here. So what we want to know from this heat map, we want to see which variables are most highly correlated with the sale price, right? Because we want to be able to predict sale price given a few variables. So we want to see in this sale price row here, which of these variables are the darkest, right? I don't know if you guys can see. If you guys can see, you can type in chat box. Okay, it's okay. So the darkest ones that you can see are, yeah, exactly, overall quality, and there's also greater living area and garage cars. Those are the three variables that we're going to use to predict the sale price. So, time for regression. First of all, what is linear regression? Linear regression is a type of predictive analysis in machine learning. Essentially, what we're trying to do is we're trying to predict an outcome based on given input. So the outcome is Y, and the inputs are X. So just like in algebra, the Y is the dependent variable and X is the independent or explanatory. So when we say we want to create a regression model, basically what we're trying to do is we're trying to find a line of best fit to fit the data. So there's two main types of linear regression. There's simple linear regression and there's multiple linear regression. So simple linear regression means one input variable, one output variable. Multiple linear regression is multiple input variables, but still one output variable. So how do we find that line of best fit? That's the question. So you know that from algebra, the line of best fit equation is y equals mx plus b, right? You know that m is the slope. Okay, so y is the output, x is the input, right? And then m is the slope, the slope coefficient, and b is the y-intercept. In machine learning, it's pretty much the same, except there might be multiple inputs, so it's essentially the same thing, just different names. So here, y of x, or also f of x, right, is equal to weight times input for all of the inputs plus this W0. W0 represents the intercept here. It's the same thing, pretty much parallel. W is the weight coefficient, just like M is, and X is the input, just like X is over here, and Y is the output. So, but what we're going to do just for today is to make, we're gonna get rid of this variable here, this intercept, just to make it easier to code. So the way we do that is by adding a column of ones to each of the inputs. So why would we do that? I'll show you why. This equation up here, this equation, you can rewrite that as the dot product. The dot product is another type of math function that's used on two lists of numbers of the same length. So here, w dot x turns into w1 times x1 plus w2 times x2 and so on until wn times xn, right? So we can rewrite this equation as this. And then, okay, here's an example of using the dot product. So w, let's say w is equal to 234, x is equal to 432, and w0, the intercept, is equal to 5. So if I ask you to compute y, then you'll see that you can do that easily with this formula, right? You'll say 2 times 4 plus 3 times 3 plus 4 times 2. You just multiply each of the values in each of the vectors in order. And then you add the bias. And you compute that and you get 30. So to simplify this, instead of thinking of y as a function of the slope dot the x plus some other constant, we're going to just think of it as the dot product of these two vectors. So the way we do that is we add 5, or we add the bias, the intercept, to the weight vector, and then we add a column of 1s to the x vector. So if you see here in bold, we added a 5 here and a 1 here. So now we don't need to use W0, and we compute it, and it's the same exact thing. You get the same. So now we're going to write all this in code. So essentially, in machine learning, the main idea is to reduce the error with each step of training. We're trying to reduce the error by repeatedly running our model through training. So we start with some random values, and then we improve on that model. That's the basic idea. So this first function over here, for those of you who don't know, a function in coding is basically, it's what it sounds like. It's just like a bunch of commands that you call on some inputs that will return an output, right? That's what a function is in coding. So here, this function that I've written here, and I've commented it with the hashtags. Hashtags in coding in Python mean comments. So this function here is called loss. This is going to be our error to evaluate how bad our current weights are, right? This is what this function is going to do. So given a bunch of predicted values and actual values, we're going to find the mean squared error of between the predicted and actual values, right? So we're going to find the error, and then we're going to average them by dividing it by the number of the length of the list, essentially. And then we multiply it by half for a special reason. I'll explain later. Then here, this function over here, it's called evaluate prediction. I define it to be called evaluate prediction, and it takes in some inputs and the current weights, and it returns the dot product of the inputs and the weights. That's what I showed you earlier, right? To simplify it, these weights include the intercept. So the weights again, weight is slope, right? Weight just represents the relative importance of each column. Just like how in a weighted average or a weighted sum, you give importance to different variables, right? In coding, it's the same exact thing. So we have our loss function over here. Loss function is the loss function that we're using here is called mean squared error, and it's a type of evaluation metric that's used to evaluate the quality of a certain machine learning model. And then we have our evaluate prediction, which is just going to compute this function. Sorry, not actually this function in code, right? So we have these two functions so far, and then we get into the complex stuff. So this function over here that I'm about to show you, it's called gradient descent. And okay, essentially this is the part where we try to reduce the error, right? I'll try to explain it to you. Some of you, I'm not sure how much math you know, but essentially, if this is the cost or loss, as it's called, and this is the weight, the value of the weight. So on the x, if you look at this graph here, it's really helpful. The x values represent all of the weights, right? And then the y values represent all of the losses, all of the costs, as they're also called. So if we plot this, if we plot all of the weights as against cost, we'll see that there's a certain weight value that has the lowest cost, right? So we're trying to find that weight value. So if we start off with like some random value, I don't know, let's say we start off with, let's say this x-axis goes from 0 to 10, and the optimal weight value is at around 5, right? But we don't know that yet. We're going to try and test this out. So what we're trying to do is we're trying to inch towards this optimal weight value, right? We start with some random value, and we're trying to find in which direction is this optimal weight value. So the way we do that is by finding the derivative. What is the derivative? So you know that in algebra, a slope is the rate of change, right? How steep is the graph? A derivative is the same thing essentially. It shows how steep is the graph, but instead of it being a line, it's a curve. So if you were to imagine this curve as a skate park, this curve as a skate park, you would imagine a skater like skating down. On the left side, the skater would be going down really, really fast, right? When the skater is going down really, really fast, that means that it's a negative value, negative derivative. On the other side, at around 5, at the minimum, he's pretty much slowing down over here, right at the bottom. And then as he goes back up, on the other side, on the right side, he will slow down a little bit more because it's really steep and that's a really positive slope. So this derivative is called gradient. Also, when you use it at one particular point, it's called a gradient. And what we're trying to do is we're trying to step in the opposite direction of the gradient. So if you see at this point here, where they plotted the dot, that dot represents the initial weight. And if you calculate the derivative, the slope, how steep is the skater skating at that point, right? That's that dotted line, that dashed line, that represents the gradient. And then what we're trying to do essentially is we're trying to go in the opposite direction. So this gradient line is pointing upwards. We want to go downwards. We want to go in the opposite direction because the opposite direction is going to be the direction towards the minimum. So that's essentially what a gradient is. And this is the formula for calculating the derivative. I'm not going to explain it too much because you need calculus knowledge to do that, but that's essentially the formula. But what we do is we evaluate the predictions using our method from before, our function. The function that we wrote over here, we can call it in this new definition of a function. And we set that equal to the predictions. And then we find the error, which is the predictions, the initial predictions minus the actual outputs, right? So we are going to find how bad are the current weight values. Then we run it through our gradient function. And then we return our new weights. Our new weights are going to be scaled by this learning rate. Essentially what a learning rate is, it just tells you how fast or how quickly should the model learn. How big of a step should the initial weight take. So this function over here, gradient descent, it will take one step in the direction of the opposite gradient. I hope that makes sense. It will take one step in the direction of the opposite gradient. So that's what this function does. Now, for training. So when we train, as I said earlier, training is just repeated gradient descent. You're going to repeat taking steps down this path until you get to the minimum value. So here, I have my definition of a function. I have the parameters, the arguments here. Inputs, these are the inputs, these are the actual outputs. Number of iterations means the number of times that I'm going to run gradient descent, the number of times that I'm going to try to keep improving my model. And then the learning rate, as I explained earlier, the learning rate, it shows how fast should the model learn. So if you want to compare iterations and learning rate based on how effective the model is, what you want to do is you want to slow down the learning rate so it doesn't take too big of a step. What will happen is if you have too high of a learning rate, then your step might jump from the right side of the curve all the way to the left side and skip completely over the minimum value, right? And you don't want that to happen. So it's better to have a lower learning rate. And it's also better to have a higher number of iterations. These iterations are also known as epochs. And the more iterations that you have, the better that your model is going to predict the values. So, the first step in training is to generate some initial weights. These can be random. I initiate them as zeros, so these are all zeros. That's what this numpy.zeros means. This is the numpy, the package that we imported earlier. Then I have this list here. A list is a type of Python data structure that I'm going to use. It's called loss history. And I'm going to use it to show you later how well our model learns, because you'll see that the loss will decrease as the number of iterations increase. So here, in this next line, I have a for loop that will loop through iteration number of times. So you pass in a number here. Iterations is going to be a number. So let's say it's like 100 or something. You're going to repeat gradient descent. You're going to keep stepping 100 times until you get to the minimum. That's what iteration is. So when I say this Python for loop, that's what it does. So yeah, so my steps are evaluate the prediction with the current weights that I have, then calculate how bad my current weights prediction are, append that to this list, this Python list over here, called loss history, and then I take one step in the direction of gradient descent. So I'm going to repeat this multiple times. This is kind of complicated, and actually, yeah, okay. Before I go on to training, or before I show you how we'll actually use those models, I want to make sure these 4 methods make sense. So I'm going to repeat these 4 methods, and then I'm going to ask for any questions. I'm not checking the chat box right now, but afterwards I will. Okay. So I have these form. These are the 4 functions that I created. A function in coding is a bunch of commands that will take in inputs and return. It'll perform some operation on those inputs and it'll return an output. So this first function over here is pretty simple. It calculates the loss. Loss is a function. It's also called the cost function, and it'll basically tell you how bad are your predictions, and it uses the mean squared error to calculate this. That's the first function here. Calculate loss. Then I have evaluate prediction over here, which is just going to perform this function right here to evaluate the prediction of your current weights dotted with the inputs. Then I have gradient descent over here, this function. It'll use the derivative function, which is basically the slope, how steep is the curve, how steep is the curve, and in what direction should I go to reach the minimum? In what direction should I go to reach the minimum, the weight that will give me the minimum cost, the minimum loss? That's essentially what gradient descent is. So this function over here will take one step in the direction of the steepest descent. That's what this function does over here. Then for training, essentially what I do is I repeat this process again and again and again to see, okay, okay, I'm going to keep taking steps in the direction of steepest descent to see which weight will give me the lowest cost. So feel free to ask any questions right now. Oh, can you guys hear me? Can you reply if you hear me? Okay. Okay. So I hope that you heard like at least some of that explanation. If you have any questions at all right now, feel free to ask. So I explained these 4 functions. I'm moving closer to the mic now so that you guys can hear me better. So I have calculate loss. This function over here will take in the predicted values and the actual values and compute the error and return the average error. This is called the loss function or a cost function. Then my evaluate prediction here, this returns the dot product of the inputs and the weights, as I showed you earlier in this function, right? It returns the dot product, and you don't need the added intercept here, right? Then here, gradient descent, the essential idea is to take a step in the direction that will bring you closer to the weight that will give the minimum cost. You're trying to go closer to the weight that will bring you the minimum cost. And then for training, you just repeat this process how many number of times that you want. And for training, what you want to do is you want to increase this number, the number of iterations that you repeat, the number of epochs that you repeat, but you also want to lower the learning rate so that you don't jump over the minimum. Because if your learning rate is too high, then you jump over this minimum. So do you have any questions so far? Okay. If you don't have any questions, I'll continue. And just as a reminder, I can't read the chat as I am presenting. So yeah. So now we're going to use these functions that we've created to train our models. So the first step that we're going to do is we're going to pick a variable, right? As we mentioned earlier, ground living area was one of the variables that caused us to have the highest correlation with sale price, right? So we want to pick live area, which stands for ground living area, as our x, our input, or explanatory variable. Then what we're going to do is we're going to use this function. This is one of the imported functions. What this function does is it's going to split the data into training and testing. As Yash mentioned earlier, that's one of the steps of machine learning, is to first train and then you test it on a validation or testing set. And one of the parameters of this train test split method that we've imported is called test size. And what we set test size to over here is 0.2. That means that 20% of the data from this data frame, the one that I showed you at the top, is going to go into our test set, our validation set, and 80% of it is going to go into training. So that's the first step. We split into testing and training. Then I'm going to standardize both the training and the testing data. So I standardize the data, the inputs, by calculating the z-scores. That will standardize it so all of the x values are on the same scale. And then here, this line over here, this line will concatenate the column of ones. That's what np.c means. np.c, NumPy has a function called c underscore, which will it'll add, concatenating means to add. So it'll add that column of ones to the inputs, as I mentioned earlier, to get rid of the need for the extra variable for intercept. So instead of using an intercept as well, we're just going to use the dot product of the two variables. So I repeat that for both the training and the testing data. I standardize and I concatenate the column of ones, and then I run my training model function. This training model function will be run on the standardized training data and with the outputs of the training data. So these standardized training data, this is going to be the area of the houses. So the houses, they might have area like 1,000 feet or 2,000 square feet. And then the Y train, what we're trying to figure out, Y is the outputs, the actual sale price of the house. So we want to be able to plot this kind of line of best fit for the data. And we're using 1,000 iterations, 1,000 epochs, with a learning rate of 0.01. So if you remember, I said earlier, a higher number of iterations is better, as well as a lower number of a lower learning rate. So now I run this through my training model that I wrote, my train model function that I wrote earlier, and then I print out the final weights. Okay. Does anyone have any answers to any guesses as to what these weights might mean? What do you think that these weights might mean? This 56,181 and this 108,473. So if you remember, our goal here is to create a line of best fit, right? And to do so, we're finding the weights and the intercept, right? So what do you think these numbers might mean? This 56,000 and this 180,000. Yeah, essentially. So if you remember a line of best fit function or equation, it has the y equals mx plus b, right? And I showed you before that in machine learning, we have to adjust for possible multiple inputs, but because I'm showing you simple learning right now, there's only one input. So this essentially is your m. This 56,000 is your m. And then this 180,000 is your b, the intercept value. And so this number is going to be multiplied by the ground area and then added to this number to find out, to estimate the sale price of the house. So now, if you remember, I returned, when I made this function here, train model, I returned the weights, the final weights after training a bunch of times, as well as this list for loss history to show you guys how the losses decreased over time. And what I can show you here is that using the PLT, I don't know if you remember, but PLT from the top, PLT is the matplotlib.pyplot package that I imported to be able to plot graphs, to plot figures. So what I do here is I plot the loss history list, and I give it a title, a label for the x-axis, a label for the y-axis, and then I say dot show so that I can print it in the output. So if you'll see, this loss function is decreasing quite a lot, actually. It decreased from about 2 to around 0.2. That's where it converges. That's the word, converges. And what you'll notice is that it decreases much more in the first 200 or so iterations, and then it starts to decrease a little bit less and less until you hit 1,000, which is my cutoff. And this is because at the beginning, because I used random values or I used zeros, right, for my initial weights, the error is super duper high. And because the error is super duper high, then the steps are also going to be super duper high. And it's going to be easier to fix those steps by like a large margin, right? But afterwards, then it's kind of just fine tuning our weights to find the absolute minimum. Yeah, so you can notice how well repeated training, this shows the importance of repeated training. Because we repeat training so many times, that's what reduces the loss. Now what we're going to do is we're going to plot the model that we just created, this y equals mx plus b, or weight plus bias or intercept. We're going to plot it against the original training data. So the way I do this is, again, with the PLT package, I scatter the X and Y training data in red, and then I plot the X training data, and instead of Y now, I'm using my predicted values. Evaluate prediction is the function that I wrote earlier to evaluate the predictions based on the weight. So after I've calculated my final optimal weights, I input it into this function that I've created to predict all of the weights, and I color that in blue. Then I give it a title as before. We're going to graph sale price versus living area with our training set. Our x-axis is going to be living area, and our sale price is the y-axis. And I show this, and you can see how well we've plotted the data. Yeah. So yeah, you can see that because this line is positive slope, that means that higher living area is going to be more expensive, which makes sense in real life, right? And as for the application that I said earlier, as a buyer, you don't want to buy this, or sorry, you'd want to buy this house over here as an outlier. You see this house at the bottom, the outlier. You'd want to buy that house because you'd be getting a huge house, almost 6,000 square feet, for a pretty cheap price. And you can see because it's below the line, it's good for the buyer. And if it's above the line, it's good for the seller because the seller would make a greater profit. But because these values are so dispersed, our line of best fit it's good, but it's not as good as a network might be because a network, as we're going to talk about later tomorrow, is going to be a better predictor because linear regression it's good, but it's like it only works if your data is actually pretty linear, if it has a linear correlation. And then, so we did this we plotted it against the training set, and we saw that it looks pretty nice. Then when we do the same thing and we plot it against the test set, we see that it still looks pretty nice. It kind of looks like the test set is more dispersed, but it's only because this is only 20% of the data, and it doesn't look as like clumped up together as the 80% of the data over here. So we talked about simple linear regression. Simple linear regression takes in one input, which we used living area because it had a high correlation in the heat map. And we plotted against sale price, which is our dependent variable, and we found the line of best fit, essentially. So we found the best linear regression model that would match this data. And then we plotted again against the test set to find how well it does on a data set that it's never seen before. It hasn't trained on this data set, it trained on the previous one. Because, okay, so we use this test set to make sure that we don't have overfitting, like Yash mentioned earlier. Then for multiple linear regression, essentially it's the same exact process, except you have multiple input variables. So here, instead of just using greater living area, ground living area, we're also going to use overall quality and garage cars. So now, okay, so I can actually plot this later as a line of best fit because there's 3 variables and then another sale price variable, so that would be 4 dimensions, and obviously I can't plot that on a computer, but you'll see that it's the same idea. So I standardize, and then I concatenate all the ones to the inputs, and then I train. I use the same parameters that I used earlier, 1,000 epochs, 1,000 iterations, with a learning rate of 0.01. And then I print out my weights now. And you'll see that before I got, earlier with the simple linear regression model, I got two values for the weights because I used I used one input. I had one weight value for the ground living area variable, and then I also had the intercept. And then now again, I have four weight values. So these 3 are for these 3 input variables, and then this is my intercept. So what do you think these values might mean in context of these variables over here? Greater living area, overall quality, and garage cars. What can you tell by looking at this one? So this one says 26,000, while this one is 37,000, while this one is 16,000. Why might that be? Let me repeat the question. Why might Why might it be that the weights are different for the different variables? Does anyone want to take a guess? Okay. As I said earlier, the weights represent the relative importance, right? So when we see that this value over here, 37,000, which corresponds to overall quality, is higher than 16,000, which corresponds to garage cars, that might mean that overall quality is more important to computing the value of the house than garage cars. So because garage cars is only worth 16,000 of a weight, and overall quality is worth 37,000 of a weight. So when you make this weighted sum, you're going to give more weight, more emphasis to overall quality. So essentially what that means is that garage cars is not as important in determining the sale price of the house. And then here I plot the loss function again. You'll see the loss function, and we see here that the loss is still decreasing with the number of iterations, but because I have more information, because I have 3 variables and not just 1 variable, I'm actually able, if you look really closely, you can see, I'm actually able to reduce the loss to 25 before 200. Before the previous graph, the previous loss graph that I showed you, it also converged to the same value, but it didn't converge as quickly. So what we get from this is that when we have more information, then we're able to make a better predictor that will reduce the loss after fewer iterations. So now that I've taught you guys what goes behind training a linear regression model, we're going to use an sklearn package, the scikit-learn, to do so automatically. So we're going to use this sklearn package called the sub-package called linear model, and we're going to import the linear regression function, or sorry, the linear regression class from this scikit-learn package. So what we do here is we create a linear regression object of this class, and we just say fit the data, the training data to the output data. And what this fit function does is essentially the same thing as our train model function that I showed you earlier. So what we were able to do, what we were able to code in a bunch of lines, this function lets you just do automatically. You just say regressor equals, and then you just fit the data. That easy with the packages. And then when we print the coefficient and the intercept, the coefficient here is the slope, or the W, the weight, and the intercept is the same thing here. You'll see that our guess was pretty close, right? If you remember, or if you scroll back up from the initial, this is the simple linear regression model here, and our values are pretty close to theirs. Remember, ours was like 56 or 57,000, and our intercept was 180,000. Yeah, so we can say that our training model function that we created is pretty much the same thing as this fit function from the scikit-learn package that does so automatically. So what I do here over here is I essentially plot the model as a line of best fit, as I did earlier, and instead of evaluate predictions, the regressor class has a predict function that we can use on the standardized X-train data. And I didn't mention this earlier, but standardizing allows the data, when you perform gradient descent, it allows gradient descent to converge more quickly, to find that minimum more quickly. So I plot the training data in red and the line of best fit in blue, and I do the same thing that I did before, and you'll see that this graph also, this regression model also is plotted pretty well against the training data. So that is basically all that I have, and I have a few discussion questions over here. So our first question is, in your own words, what is a data frame? You can type it in the chat box. You can also scroll back up. I'll send the Kaggle notebook again. Here. What is a data frame? Yeah, exactly. Yeah, it's essentially a table. Yes, Porna and Ellis and Chirag. Sorry if I'm pronouncing your names wrong. It's essentially a table, just like the spreadsheet that I showed you guys, but it's stored as a data structure. A data structure is a special format of data encoding, and basically, yeah, it allows you to call each column of values and store them in another variable, and they're used a lot in data analysis and data science. So the next question here is, what's the significance of the heat map? The heat map that I showed you guys? Yep. Yeah. So essentially, it showed the correlations or the connections between each of the columns. And what we used that for is we used it to see which of the values, okay, yeah, which of the values are most correlated with sales price. So a heat map, okay, I don't know if you're responding to the heat map question or another. Okay, yeah. Okay, I can explain that again. So a heat map is a visual representation, and it uses color to show the correlation, right? We use color, but in general, it's not just used for this. It's used in like statistics, biology, bioinformatics, a bunch of different fields. But what it shows is it shows data, but instead of using numbers, it uses colors to show trends. So for example, heat maps are used in websites with businesses. Oh, sorry. Can you mute your mic, please? Okay, thank you. Please mute your mic. It's echoing, sorry. So one example of heat maps is they use it in websites to see which areas are being most clicked. So if a button is being clicked the most, then it'll pop up as like red on the heat map. So what we used it for here, is also as a color representation. And what we tried to do is we tried to see, okay, which of these, okay, you have this this bar on the right side, right, of the screen, which shows you the correlation. Essentially, okay, let me draw it up for you guys. Here. So if I want to plot two values against each other, right? If I want to plot these two values against each other, let's say I'm plotting height and weight of a person. This is not for the house, but this is for general. If I want to plot these two values, there's going to be some sort of positive correlation, right? Let's say height and weight of a class of people. And there's a positive correlation because taller people might weigh more, let's say. And so this here is going to have a correlation coefficient of a positive value, and it's going to be close to 1. It's going to be close to 1. the correlation coefficient here, it's called R, is going to be close to 1. So let's say it's equal to like 0.9 or something, right? Because there's a positive correlation. If it was the other way around, I can't think of another example right now, but if the graph looks something like this, then R is going to be a high negative value. So this is going to be negative 0.9. And then if the graph is kind of just random looking, if it's random looking, R is going to be close to 0. So let's say like 0.1 or something, because there's not much correlation between these two. So positive correlation means a high R value, a high correlation coefficient. Negative correlation means a negative value, a high negative value, and then no correlation means or like a value closer to 0. So okay, here, yeah, that's what we used it for, to find out which variables should we use to evaluate the sale price. In further machine learning, you'd actually code another machine learning algorithm to determine which values affect sale price the most. But because this is just a beginning workshop, we're going to just eye it manually. Oh yeah, so I showed you how, like, correlation, it's actually statistical, like method, but yeah, the reason why we're using it here is because we wanted to see which of the values, because there's 81 values, right? And if we use all of those values in creating our machine learning model, it would take too long, right? It would take too long to train. So I just wanted to find a quick way to see which of these values affect sale price the most. And that's the essential idea. Okay. Does anyone want to summarize? Okay, yeah, I'll just go with other clarifications because we don't have that much time. Can you go over exactly what weight is? Yeah, it's exactly that. Yeah, it's how much does the x value affect the y value? So for example, when we have multiple inputs, like in the multiple linear regression model, we have multiple inputs here, right? Okay, we have multiple inputs here, right? We have greater ground living area, overall quality, and garage cars, the number of garage cars. Those are different columns in the data frame, in the data set, right? And then when we see this here, when we see these different values, this means that when we're calculating this function, when we evaluate it using the equation that I showed you near the top of the notebook, you can scroll up there. This means that we're going to multiply the living area, the standardized living area. These are actually all standardized. We're going to multiply that by 26,000, but then we're going to multiply overall quality by 37,000 because overall quality has a bigger effect on essentially how it affects the sale price. So overall quality is more important in determining how the price of a house. And we can see that because I think overall quality compared to garage cars and the heat map, overall quality is darker. Do you have any other questions? Because we have to wrap up soon. Okay. If there's no other questions, then we can close. I think Lucy is going to close.
Awesome. Thank you so much. Give me a second. Thank you so much, Evan. I really enjoyed listening to your AI presentation. I definitely learned a lot. Guys, if you are still here, I just have a couple links to send out. So you can visit our website at dmvhacks.org or helyxscience.org, and their feedback form is there. Before you leave, though, Pranav is going to tell you guys about what we are going to be doing tomorrow. And if you still have any questions, feel free to stick around and we will answer them.
Yeah, so tomorrow we're going to be going into deep learning, which is
You
more
might be on mute, right? No, never mind.
Oh, yeah. Yeah, so tomorrow we're going to go into deep learning, which is more of a modern field of machine learning. We're going to talk about image classification and how to deal with problems like overfitting and data preprocessing and stuff like that. Also, we have our guest speaker tomorrow, Krithik Ramesh, and he's going to present his ISEF research like Yash mentioned earlier. So make sure to tune into that tomorrow.
Yeah, just looking at the questions in the chat. So tomorrow it'll be the same time. It's going to be either 3 to 4:30 Pacific time or 6 to 7:30 Eastern time. Yes, we will send the presentation link. We can send it in the chat, but we'll also send it through email. We will also send the web ID tomorrow as well through your email. If you guys have any questions, just like in general or about AI, like feel free to ask, because we have Eban and Pranav here and Yash, and they can definitely answer your questions. Thank you, Lily. Thanks for coming, guys. Thank you, Dante. Thanks, Jesse. Thank you, Chloe. Thank you, Justin. Bye, guys. Thank you, Weston. Thank you, Ashley. Bye, Joey. Thank you. See you tomorrow.
Should we stop the recording now?
Yeah.
Okay.
I don't know how though.
This conference will now be recorded.